All right, hello everyone. So as promised, this is a lecture recording on the lecture from October 5th, 2022 for Comp 330. I thought I would re-record it just so that I could incorporate some of the questions that students had asked. So I'll start off how I started off the original lecture with some reminders. So far what we've seen throughout the course is that we've had an alphabet, which has been non-empty, and we've had a language, which is just a subset of sigma star, where sigma star is just a set of all strings over the alphabet sigma. And what we said is that we've looked at ways for proving that a language L is regular, right? And so we did that by using a couple of if and only if statements, right? So the first one was a language L is regular if and only if there exists a DFA M such that the language accepted by M is L, right? So then for the first few lectures, we saw how to create DFAs to recognize languages, right? And then we moved on, and we also saw the notion of non-deterministic finite machines, or finite automata. And so we saw that if there is an NFA N that recognizes the language L, then this also means that L is regular. And this is also an if and only if. And you'll remember that the reason why this is true is because there's a one-to-one correspondence between, well, there's a correspondence. I won't say if it's one-to-one exactly, but there's a correspondence between DFAs and NFAs, where, a DFA is actually just an NFA that doesn't use non-determinism, and we can take any NFA and then convert it to a DFA. And so the family of languages accepted by NFAs is actually exactly the same as the family of languages accepted by DFAs, right? And so this shows that these two machines accept the same exact family of languages, right? And then the other thing we saw to show that a language is regular is using regular expressions. So we saw that if there exists a regular expression R, such that the language described by R, which I'll use the notation L of R, but you could also use precautious notation R hat. If this is true, right, if the language that R describes is L, then then this also shows that L is regular. And the reason why we could do this is because we saw that any regular expression can be, say, converted to an NFA, and then we can convert that NFA to a DFA, and then any DFA can be converted to a regular expression, right? We saw another algorithm for that. Okay, so that was sort of the first 3-4 weeks of the course where we were trying to prove how languages were regular. And then we saw that not all languages are regular. Like, for instance, if we have the language ANBN for n greater or equal to 0, then this language is not regular, right? The intuition being that you need an infinite amount of memory because you need to, for any string that you want to accept, so for instance, if you have the string A2B2, you need to remember that you've seen 2 A's and then check that with the number of B's you've seen. But because this number of A's that you've seen can grow arbitrarily, right? The string can be arbitrarily large, then your machine has to have an arbitrarily large number of states to consider all these possibilities. And so you essentially need a machine that has infinite memory, which is impossible. Okay, so that was the intuition, but to actually prove this, we used the, so to show this, we use the pumping lemma, right, with the pumping lemma. Okay, so what did the pumping lemma tell us? It told us that if L is regular, then L satisfies the pumping lemma, right? I won't write it down again. And so essentially what we did is we used a proof either by contraposition or by contradiction that said that, okay, well, suppose my language, say, is regular, right? Then I can show that L doesn't satisfy the pumping lemma, which is a contradiction. Or we could also use this contraposition idea using this demon game, right? So both contradiction and contraposition lead to the same result of showing that, for instance, you can use the pumping lemma to show that an bn factorial for n greater or equal to 0 is not regular using the pumping lemma. Okay? And so then we saw during the lecture that there's a problem with the pumping lemma, right? So the pumping lemma has a problem, and that problem is that there are some languages, L, for which you can show that the language is not regular using the pumping lemma. So for instance, if you take this language, AI, BJ, CK, where if I is equal to 1, then J is equal to K, right? This language here, which hopefully you see isn't regular, right? Because this language is kind of like A star, B star, C star, except that if I have A1, then I have to have BN, CN, right? So it's like A star, B star, C star, except that I have this special case, right? And so here I need to do this thing where I remember an arbitrary number of B's and then match them with C's. And so intuitively, you can see that this isn't regular. But if you try to use the pumping lemma, it won't work. Okay, so okay, and so I'll post a note to show you why exactly that doesn't work. But essentially the idea is if you try to play this demon game, the demon picks the pumping length P, then for any choice of string that you make, you can always be defeated. That's the idea behind why this pumping lemma argument never works with this particular language. Okay, and so then we saw that this doesn't mean that all hope is lost, and there are some alternative solutions. Okay, and so one alternative solution that we saw, or that we talked about, is, for instance, using closure properties. So if we assume that for the purpose of deriving contradiction, that L is regular, and then we intersect it with, let's say, L of A1, B star, C star, then this will give me A1, Bn, Cn, and this might be easier to use the pumping lemma with, right? And so we saw that there are some tricks to make things easier to prove that they're non-regular, but this closure property is kind of annoying because you have to think of the exact closure property to use, right? So if you use something like the complement, it might not work as well, okay? And so that was the way that I had motivated discussing the Myhill-Nerode theorem, because that's another alternative solution. And so this actually isn't the primary reason why we even look at Myhill-Nerode. There's another one that I didn't even have the chance to discuss in class, but that I'll try to discuss in this video, okay? And that's actually related to the notion of minimal DFA. So not only can we use it to prove that a language is regular, or not regular, right, depending on what the language is, we can also use it to prove that there is a unique minimal DFA, and we'll see that in a second. Okay, but before that, we need to go through some definitions, right? So let's do that. Okay, so the first definition we saw was about string concatenation. Okay. So suppose we have an alphabet which is not empty, and we have two strings x, y in sigma star. Okay. Then the string concatenation, which we either write x dot y or just xy, is the operation of appending y to x, right? So this is not the most formal definition, but you get the idea, right? So you have a string x, and then you stick y to the end of it, okay? And so the reason why we wanted to remind you about string concatenation is because it satisfies these two very interesting properties, right? So the first one is that string concatenation is associative, meaning that if I have a string x and a string y, and I concatenate these guys together, and then I take this string and then append z to it, right? So I have three strings. Then this result is a string, right? And so actually this resulting string will be the same as if I had started with concatenating y and z and then appending that to x. Okay, so that's what we mean by associative. And the other property of the string concatenation is that it has a unit element, right? So this unit element, which we denote in this course as epsilon, is just the string for which if you take epsilon and then some string x, it's the same as taking x and then concatenating with epsilon, because in both cases, if you stick no letters to x, you just get back the string x, right? And then there's this extra technical definition that you don't really need to know about for this specific course, but it's related to like algebra and group theory, which is known as a monoid. So a monoid is just a triple of mathematical objects where the first element is a set, the second element is an associative binary operator, and the last element, or the last part of this triple is a unit element, right? And altogether this makes up a monoid, okay? But this is just more like an FYI than anything else. All right, and then we had other definitions that were related to equivalence relations. So I'll go through these a bit quickly. So I'll write EQ just to make writing equivalence shorter. So what's an equivalence relation, right? Well, suppose we have a set X and we just have a binary relation, which actually is just a subset of X cross X, right? Then we say that this relation R is an equivalence relation if it is 1 reflexive, 2 symmetric, and 3 transitive. Right? So quickly, this just means that for every x, x are x, for every xy, x are y implies y are x, and then here for every x, y, z, x are y and y are z implies x are z. Okay? And what does an equivalence relation do? Essentially, it takes this set X that you have, right? And it partitions it into equivalence classes, right? So I have these equivalence classes, right, which have a more formal definition. So the definition of an equivalence class, right? Well, again, suppose you have a set X, you have R, which is a subset of X cross X, but now R is an equivalence relation. Then an equivalence class of R is just a set of elements, which we'll denote with a square bracket X. X is just a representative, so a representative of this equivalence class. And then I'll use subscript R just to make clear that it's for the relation R. And then this is actually just a set of elements, right? So it's a set of elements in X for which these elements are all related to X and essentially to each other, right? So you could think of, let's say, this is an equivalence class, right? Because all of these elements in here are related to each other, right? Okay. And then the last thing that we talked about was the index, right? So the index of an equivalence relation is the number of equivalence classes of an equivalence relation. So the number of equivalence classes of an equivalence relation R is its index. Okay. So for instance here, if this is my set X and I have 1, 2, 3, 4, 5, 6 equivalence classes that make up X, then my index is equal to 6. Okay. All right, so that was just a reminder definitions. Now we can actually get to some newer definitions. And so the first one is going to be specific to equivalence relations, and it's going to be called right invariance. Okay, so again, suppose I have a non-empty alphabet. Then we say that an equivalence relation R over the set of all strings, right? So sigma star. We say that this equivalence relation is right invariant if, and only if, of course, because this is a definition, for every pair of strings, if this pair of strings is related, then any other string that you stick to X and you stick to Y will also be related, right? So that's why we say it's right invariant. Invariant just means that it's not affected by this operation of sticking Z to X and Y, and then right because we're sticking the Z to the right? So both of these words together form right invariance, which is a definition over an equivalence relation, right? So it can't be just over a relation, it has to be over an equivalence relation, okay? That's, and in this specific case, it's over strings, okay? So now that we have this definition, we're gonna look at two equivalence relations that satisfy right invariance because they're going to be useful for proving the Myhill-Nerode theorem. Okay, so what's the first example? So the first example is the equivalence relation Rm. So to define this, I need to fix a DFA M. Okay. And so I fix a DFA M, and now this is how strings are related with this DFA. So for every xy in sigma star, so two strings are related if and only if when you give them to the machine M, they end up in the same state, okay? Right, so this is just saying that if you give x to M, right, so you start at Q0 and you read x, then the extended transition, right, so where you end up at the end of reading x is going to be the same as where you end up when you read y, okay? So, first of all, this is just a relation for now, right? So the first thing would be to show that this is an equivalence relation. I won't do that because I didn't do it in the lecture, and I think it's relatively easy to check. What's more interesting is to see that this is a equivalence relation that's right invariant. Okay, so why is it right invariant? Well, I'm just going to use a picture to show you why it's right invariant. So imagine I have a machine M, which is fixed, right? So it's a DFA. It has an initial state Q0. And then I know that two strings x, y, sigma star, I know that these two strings are related, right? So essentially this means that if I read x, I go to maybe the state Q. And because x and y are related, when I read y, I'm going to go to the same exact state. Okay? And so for this relation, right, to be right invariant, then because x and y is picked arbitrarily, then if I can show that for any other string z, xz will be related to yz, then this will have shown that this relation is right invariant, right? So this is essentially what I want to show, right? But this is naturally going to be true, right? Because imagine I just read x and now I read z. So now maybe I go to state P. Well then, if I read xz, because this is a DFA, if I read xz, then I'll go from Q0 to Q, and then from Q to P, right? But then if I read y from Q0, then I'll go to Q, and then if I read z, then I'll go to P. So that means that xz and yz both go to the same state when they start at Q0, right? So in other words, this means that delta star Q0 xz, right? So when you start your machine at Q0 and you read xz, this is the same as when you start your machine as Q0 and you read yz. Okay? And so because this argument was over an arbitrary pair of strings, well, this shows that any pair of strings that are related, if you stick a string z to them, whatever string z to them, they'll still be related. These two new strings, right? And so that shows that this relation is right invariant. Okay, so that shows right invariance for this relation. Now, we defined another relation, which you actually saw in your assignment, equivalence L. And so again, I'm going to need a non-empty alphabet, but this time, this equivalence relation is defined over a language. Well, it's defined using a language, right? It's still defined over strings, but it's using a language rather than a DFA. And so what it says is that any pair of strings are related via this equivalence relation if and only if for any other string z in sigma star, xz is an L, if and only if yz is an L. Okay, so what this is saying is if I have x and y, right, two strings, then these two strings are related if and only if for any other string that I pick, xz and yz are both in L or neither of them are in L. Okay, so that's what it's saying. Okay, so first of all, again, this so far what I've defined is just a relation. So you need to first show that this is an equivalence relation. But you did this in assignment 1, right? So you can just check the solutions for that. The other thing, and the more interesting thing, is now that we know that this is an equivalence relation, we want to show that it's right invariant. Okay, so how do we do this? All right, so let's do this proof a bit more formally than the other one, right? So in this proof, essentially what we want to do is we want to pick two strings, x, y, arbitrary strings in sigma star, and we want to show that if x and y are related via this equivalence relation, then for every other string that you pick, if you stick that string to x and you stick that string to y, then these two new strings will be related via this new equivalence relation, right? Why do we want to show this, right? We want to show this because this is the definition of right invariance, right? So this is what we want to show. Okay? Well, so how do we do that? Well, we have two strings that we've picked in sigma star arbitrarily. And now let's suppose that x and y are related. Okay? So now let's pick another string, z, right? So let's pick another string, z in sigma star. And what I want to do is I want to show that xz is related to yz, right? But now what I'm going to do is I'm going to use the definition of this equivalence relation, right? So what does this equivalence relation say? It says that two strings are related, right? So two strings are related if and only if for any other string you pick. So now I'm going to pick u. For any other string you pick, if you take this string, right? So if you take xz and then stick u to it, right? And you take the other string yz and you stick u to it, then these two strings are either both an L or neither of them are an L. Or in other words, the string xz appended and then concat u is an L, if and only if the string yz concat u is an L. Right? Again, this is by definition of this equivalence relation. Okay? So now essentially all I need to show is I need to show this, right? Because if I show this, then this is true by definition, right? Okay, so let's do that. Well, here I have an if and only if. So essentially all I need to do is show both directions, right? So I'll show the forward direction. Well, let's first suppose that xz u is an L, right? Okay, well, we know that string concatenation is associative, right? So then by associativity, xzu in L is the same as x and then zu in L, right? So this is by associativity of string concatenation. Okay, and so what does this imply, right? Well, this implies that because x and then zu is an L, right? And we know that x and y are related via this initial equivalence relation, right? But what does this equivalence relation tell me? It tells me that x and then the string is an L, if and only if y and then the string is an L, right? So this is the definition of the equivalence relation. And so by definition of the equivalence relation, if this is true, then yzu must also be an L, right? So this is by definition of this, and because we know by assumption that this is true, right? Okay, because it doesn't matter that I have zu as a string, right? Just think of these two guys as just one single string together. Well, then I know that x and the string is an L, if and only if y and then the string is an L, right? Okay, and then I just have to reverse the concatenation to get yz u in L. Okay, and this proves the forward direction, right? This proves that xzu in L implies yzu in L, and then the reverse direction is similar, right? So it's actually almost identical. Okay, so what have I just shown? I've just shown that if I have some arbitrary u, right, so because u here can be any arbitrary string, then I've shown that xzu is an L if and only if yzu is an L, right? And so by definition, right, so by definition of this equivalence relation, this means that xz and yz are related via this equivalence relation, right? And so that's essentially what I wanted to prove, right? I wanted to show that if I had some arbitrary pair of strings related via this, then any other string that I stuck to x and y would also be related, right? If I showed that, then this would mean that this guy is right invariant. And so I did show this, and so this means that, therefore, this relation is right invariant. Okay.